would not be able to produce this without them. If you have any feedback about the conference, you can go to bsides.com/feedback, or you can go on the schedule to a particular session that you have feedback on, click it, and click on the feedback survey button. Again, we have a raffle for a $150 Amazon gift card by Jim Alto that will be done at the end of the day. So if you want to submit to that, please go ahead. Again, the burning rubber smell is from a fire down the street. Nothing to worry about. We'll let you know if there's a real emergency. So I just want to introduce Craig Young. He's a security researcher at Tripwire, and he's going to be talking about Fuzz Smarter, Not Harder, and AFL Fuzz Primer. Give your attention to Craig.
All right. Hello, BSides. Thank you. Thank you for having me back again. So, as introduced, I'm Craig Young, and I am a security researcher with Tripwire Avert. I do a lot of vulnerability hunting, and today I'm going to be talking to you a bit about one of the tools that I like to use recently for hunting for bugs, fuzzing, and specifically the AFL fuzzer. So, to go through this, we're going to talk a bit about what fuzzing is exactly, how it gets used, the values of AFL, how to use AFL, how to get the most out of using AFL, and then we'll look at what you do once you've actually discovered some crashes, how you evaluate them, and figure out whether or not they're worth something, whether or not they're exploitable. And to wrap up, we'll talk a little bit about some of the results that have come out of the use of AFL, as well as perhaps some time for question and answers. So, what is fuzzing? Fuzzing at a general level is the concept of mutating input, passing it into some process, and looking for it to break. There are a couple categories of automated fuzzing that we'll go over very quickly. You have dumb fuzzers like ZZUF. Basically what you're talking about here is just blindly mutating a file and hoping for crashes to come out. We've got smart fuzzing, which is where you're going to generally devise some kind of template that's going to describe the format that you're fuzzing. So the advantage of this over dumb fuzzing is that you're going to hit a little bit more of the harder to reach places in the code. You're going to expose more features because you've got a description of the data that's being fuzzed here. One of the problems, though, is you've got to actually develop some code and spend some time understanding the format you're fuzzing. And of course, with dumb fuzzing, you don't have to spend very much time setting it up, but you're not going to hit stuff that's very deep within the code. So this brings us to instrumentation-based or coverage-based fuzzing. The idea here is that you're actually going to be monitoring how the program executes and seeing what code paths are being taken and using that to determine the value of your fuzzing efforts. The advantage here is that you have very quick setup time. You don't need to worry about any knowledge of what type of data is being parsed, and you're also going to be able to hit very deep levels of the code, as we'll see. American Fuzzy Lop is a great example of instrumentation-guided fuzzing, but it is not the only technique out there. Some of you might have used the Intel Pin tool, for example, for doing similar types of things. So, when we are fuzzing, there are a couple different mutation strategies that we will use. You want to be flipping bits, adding and subtracting different values, so basically walking through your file or your test input, interpreting sequences of bytes as different lengths of values, and going from there with arithmetic, changing around byte orders that you find when you're doing that iteration, and also inserting things like maxint and just setting high order bits, putting in generally interesting values. The advantages of fuzzing, there are lots of them. So you can be fuzzing 24/7. Right now I'm talking to you guys, but I'm also fuzzing a media parser on 32 cores. You're going to find with this process a lot of bugs that are going to escape typical code review. Particularly, we see a lot of use after free bugs that are not going to be readily visible by even very experienced programmers, but the fuzzers will kick these conditions out. And if you look through browser bugs especially, that's a lot of what you're seeing now is use after freeze. Fuzzing also gives you a way of generating a test corpus that you can use in other testing efforts. And finally, you want to be fuzzing because, frankly, the people that are trying to attack your software that you're designing or your internal systems, they're also going to be fuzzing, so you want to be on the same page as them. So American Fuzzy Lop, this is a tool that was developed by a Google engineer. Sorry if I'm not pronouncing the name correctly, but Michal Zalewski, also known as LLVM. And he developed this based on some of the research that was going on showing how you could use gcov specifically to look over a set of test cases and figure out what the most valuable test cases were based on coverage, and that this would lead to more valuable fuzzing efforts. So LLVM took this one step further and actually started fuzzing while binaries are instrumented, so that you can see the results of your fuzzing in real time. And the results here is that American Fuzzy Lop is quite effective against a wide range of different targets. So image parsers, browsers, compilers, you've got a wide spectrum of places where it's successful, as we'll see. The key benefits of this system: AFL is really fast. There's not a lot of overhead involved. It's got some features that we'll talk about that make it very effective at being able to use instrumentation and quickly discover interesting test cases. It's very simple to use, meaning there aren't a whole bunch of things that you have to tune in and stuff that really only the person who made the tool is going to understand how to get it tuned in exactly as it needs to be. And it's just overall very reliable. You don't have to worry about making tweaks here or there because you're fuzzing one target versus another. You follow the steps for using it, and it's generally going to work and keep working. Before we get into how it works, it's necessary to kind of understand what a basic block is. I'm sure most of the people in this room know that, but at a high level, a basic block is a set of instructions where you're going to enter it, and if you enter it, you are going to exit it at a specific point unless there is an exception. The way that AFL works is by instrumenting these basic blocks. So you put in a few new instructions around places where there are branches so that you're able to monitor the execution path. You can see here that some pseudocode for the instructions that are being put into the binaries. This can, of course, either be put in through compiling or through user emulation with QEMU. But the first thing I want to point out is you've got a random number here. This might seem odd, but the reason that you do this is you're going to be compiling a number of different objects and linking them together. You want to have minimal overlaps here. And then also you'll see on the second line of that pseudocode there's an XOR operation going on. And those locations, you want to have a good distribution for the results of that XOR so that it's not clustered. And having these random numbers helps doing that. When you're actually fuzzing, AFL Fuzz is going to give to the target program a 64 kilobyte shared memory region, and that region is then going to be essentially a bitmap for the code execution. It's going to be able to identify where execution came from and where it is now, so that you recognize state transitions. And then state transitions which have not been seen before, or when you have noticeable differences in the hit counts for different path tuples or these state transitions, that's going to be something that you consider interesting, and you're going to want to add that to your queue and continue fuzzing based on that. So probably can't see very clearly, but that's intended here. This is a chart of LLVM's efforts fuzzing gzip just for a couple hours on a single core. You can see in the first column there, these are all the test cases that you would reach just through blind fuzzing, through random mutations. But then when you take those test cases and you start fuzzing on them, then you can find that second level and so forth all the way up to the 6 levels here. And you could, of course, go beyond that. But just to show the kind of variety of test cases that you're going to get that you would not otherwise get through blind fuzzing efforts. One of the more interesting things that I've seen, or one of the things that got my attention rather in the first place with AFL, was a blog post from LLVM showing how he was able to just seed input for a JPEG parser with the word hello, and using that, all of these graphics that you see here were actually synthesized by the fuzzer without any previous knowledge of JPEG. So that means you went from the word hello to being able to figure out how to populate Huffman tables and create JPEG frames. It's really quite impressive. And starting to get images like this, in my experience, you can do that within a day or two, maybe 3 days. So if you want to go ahead and start using AFL to fuzz stuff, it's pretty simple. The first step you have is you need to build the AFL toolset. So it's a very standard download, extract, make process. And then the next step is you're going to need to find a target that you want to fuzz. And when you have your target, you grab the source code for it, and you configure it to use the build products from AFL. So this means that when you did that make on AFL, you're actually generating wrappers for GCC and CLang, and potentially a few other things that we'll talk about further down the line. You're then going to make your program using those compilers. You'll actually recognize what's going on, that it's using your tool, the AFL toolchains, because you will see status messages coming up telling you that locations have been instrumented. So once you've got your instrumented binary, and you've got AFL build, of course, you then take the instrumented binary and you pass it to the AFL fuzz application, along with references to some initial test inputs and a place to output your findings. So this is the most basic usage of AFL fuzz. When you're running it, you'll get a status screen that's something like this. Very nice retro look there. And if we start breaking that down, there's some important elements that you can take from the status screen. So first, in the overall results box, you've got this cycles done. What is a cycle? Well, this means that you've gone through all of the test cases in your queue and gone through a stage of fuzzing on them. You generally want to let something run for at least one cycle, typically several cycles. The color on that will actually start changing as you stop identifying new paths for long periods of times. So additionally, in that overall results box, you've got to count for the number of paths that have been discovered. So this is essentially saying how many interesting test cases have we found that represent or exercise unique code paths. You've got counts for the number of crashes, which is self-explanatory, and hangs, which is less self-explanatory. This is actually not necessarily referring to like infinite loops or anything like that, but just any test case where it's triggering a code path that exceeds the timeout that's been established by AFL or manually entered with the T flag. So by established by AFL, what I mean here is that it's going to baseline the process with the test case inputs that you gave it and determine how long it expects on average for the process to take. If it's taking too long, it's going to cut it off. You can tell it not to do this or exceed the timeout, but really what Alcantif has said is that you're not gaining any additional or much additional coverage for the time costs from that. Another important thing to look at on the status screen, the map coverage. This is indicators of how your fuzzing bitmaps are filling up. And if you see that this first number there, that's 7326 on the screen, if that drops below 200, or if it is below 200, this probably indicates that you didn't instrument enough stuff, or you're not fuzzing what you think you're fuzzing. So you should probably Control-C and check your bases again. The percentage that's indicated there, this is also a good metric. If it goes above 70%, it probably means you're having some collisions. The fuzzer's not able to effectively determine new state transitions, new paths. So you're going to want to Control-C and start reading the docs for the AFL INST ratio, which basically is just going to say when it's compiling stuff, there's some percentage likelihood that it's going to instrument any particular branch. Finally, on the path geometry, there's one field that I want to point out. That's the variable field. What this means is that when AFL runs the same test case twice, it's not getting the same execution flow. This is important because it could be implicit or implicating certain security bugs, like the use of uninitialized memory specifically. So something to keep an eye out for. As your fuzz progresses, it's going to start populating a few directories as well as creating a few files. Within the Q directory, this is where all of the interesting test cases are. So that's essentially your synthesized corpus. The crashes directory, of course, has your unique crashes, and your hangs directory, those test cases that were exceeding the timeout. When you're running a fuzz, you might run into a couple different error conditions, or blockers, if you will. The first one that you'll probably notice is out-of-memory conditions. This is going to happen a lot on some things because when you're running AFL, it's going to be limiting the memory envelope that you've got, the virtual memory available for the fuzz process. If you use the -m flag, you can increase this until you get sufficiently few out-of-memory conditions. You can also, at least on some of the older versions of AFL, disable the memory limit, but this can lead to instability within your system. If you're fuzzing something that's really a slow binary, that's going to be a big problem here too, because in case you haven't noticed, the whole idea here is that we're trying to execute the program as many times as possible to try and identify these new states. So slower binaries means less executions per second, means less interesting test cases, means less vulnerabilities that you're going to find. If you have a very big test corpus, which means like, let's say you start with 100 different images to fuzz DJPEG, that's not going to be a good thing because, for one thing, all of those test cases are going to implicitly become part of the queue. So each time you're going through a cycle, you might have 40 or 50 extra paths that need to go through a complete fuzzing cycle, or a complete round of fuzzing, which is going to be a big waste of time for you. We'll talk a little bit later about how to identify the best test cases to make your corpus effective for your fuzzing. Large test cases, finally, this is another problem area. Of course, if you have a large test case or a large input file, it's probably going to take longer to execute through your target application. And another factor to consider here, if you've got a larger file that is more bytes that potentially need to be fuzzed, so it means that the likelihood of fuzzing one specific byte in that file that might reveal a bug is going to be reduced. So you can minimize your test cases. This is something else we'll talk about in the next section. But before that, if one example of fuzzing, if you want to take Ubuntu packages, you're probably going to want to fuzz them built, configured the same exact way that they're getting shipped out in the operating system. So a very simple way to do this using apt, you grab the source, you get the build dependencies, of which you might actually want to not install the packages, but rather go through this process and build those and link against instrumented libraries and dependencies. But for each package in the source directory, typically it's enough to just go into the Debian rules file and add some export lines to set up the environment to use the AFL compiler and any other parameters for AFL that you want to specify. And then you can just do a deb build, and you will get a directory with the binaries instrumented, built the same as if they were built for the Ubuntu package. So, how do you get the most from the fuzzer? There are a number of features that AFL offers for you. The first one that you're probably going to want to use is parallel fuzzing. So, if you don't have, or if you have idle CPU on your box, you probably aren't getting the most out of your fuzzing operations. So the way to resolve this is by taking advantage of the master-slave model that AFL offers. In this model, you have one master node, typically, which is going to perform very deterministic fuzzing steps, and then you have one or more slave nodes, which are going to just perform random tweaks. The master is going to be a bit slower generally, and these slaves are going to get through their cycles quite quickly, relatively speaking. The arguments here are roughly the same, except that you're going to have -o, no longer specifying an output directory, but instead specifying a sync directory. And within that sync directory, you'll have additional directories for the names of the master and slave nodes. And under those, you have what you would expect in the normal AFL output directory. The contents, like the test cases that get discovered in the different slaves and in the master, they're going to be picked up and synchronized across the threads using a culling algorithm to identify favorable test cases to bring in. So in this way, your test cases do kind of gradually become somewhat homogeneous. It's important to note, you don't need to worry about monitoring closely each of the status screens. In fact, in my fuzzing, I generally pipe to a file, and it does not produce the status screen. It gives a little bit more lightweight status outputs, but you really just want to keep an eye on what crashes are coming up in the slaves, which there's a tool we'll talk about in a minute to do that, and also looking at the cycle count and the color of that cycle node on the master to get an idea of whether or not your fuzzing is still being productive. There is a tool included with AFL which gives you the ability to measure your computer and determine whether or not you've got resources available to keep on running more processes. Basically, this is just going to make a busy loop and measure how much time is scheduled to that process in the busy loop compared to how much time expires on the clock. You can see some sample output of what that looks like. So once you've got parallel fuzzing going and you've maxed out your box, the natural progression from that is to start distributing the fuzz across multiple boxes. So this is basically running parallel, using AFL fuzz with the master-slave model, but across multiple boxes. What you need to do here is just on the other boxes, you need to copy or periodically synchronize the queue and the fuzzing stats over to the other nodes so that everything can benefit from that. There's an example script within the AFL distribution, this sync script under experimental directory there. And there's also referenced in the documentation a GitHub project disfuzz, which gives you some nicer controls over being able to start fuzzes and keeping them all synchronized. Now that we've got our fuzz using all of the resources available and also using multiple boxes, you can continue to get some performance benefits by moving into the LLVM mode. So now, this is not currently a main mode for American Fuzzy Lop. In order to take advantage of this, you have to actually go into the LLVM mode directory and follow some steps to do a build in there. It's quite simple. You just need LLVM config on there, and of course CLang. What you're going to do here is be able to create the AFL CLang fast family of compiler wrappers, which are, rather than compiling something to assembly and then rewriting the assembler, it's going to actually do true compiled-in instrumentation. The advantage here is quite big because you're going to get to take advantage of compiler optimizations, which just are not available when you're at the point of already compiled assembly. One thing to note, when you're compiling a target with this, you will need to point it to the AFL home directory through the AFL path environment variable. But once you are using this, there are some features that AFL CLang Fast and CLang Fast++ offer that you can take advantage of to even further speed up your executions. The first bonus feature that you get here is Deferred Instrumentation. What this is doing for you, relative to the normal operation of AFL fuzz, which in a nutshell, you're using a fork server that's going to start up the process and run it all the way to the entry point main of your C application or C++ application, and then it's going to clone that and put it someplace else where it's able to keep on spawning up from that point, so you don't have as much overhead in forking new processes over and over. With the deferred instrumentation, however, you can actually tell AFL it's okay to not start or to run the process a little bit further and wait before you clone it, so that, let's say you want to fuzz TCP dump or something like, or I'm sorry, Wireshark, let's say, and you want to get past the points where it's registering different protocol handlers or dissectors, that this will actually save quite a bit of time because each time you're executing, you don't have that overhead there. There is, of course, it's important to be conscientious about where you're putting the initialization in. If you do it too late, after, say, you've started working with some temp files or started some sockets or timers, whatever it might be, you're going to have some interesting results from your fuzz. But if you do it right, it is a very good bang for the buck. The second bonus mode that we have here is AFL CLang's persistent mode. So this gives you some ability to get a little bit closer to in-process fuzzing techniques. So you're going to cut out even more of the overhead involved by making it so that you have AFL run a certain set of code within a loop. What's necessary to do here, you just have to make sure that the state of your parser or whatever you're trying to fuzz is really cleaned up. So any file descriptor accesses need to be closed, memory needs to be freed, and stuff needs to be put into a pristine state, or you need to be working with something that is truly stateless. And so you can see here the way that this happens is you use the macro AFL loop, and you give that a parameter indicating how many times you want it to go through that loop of code. A good starting point for this is 1,000. If that works well for you and you're not seeing performance hiccups or memory leaks coming on, you can bump that up as high as you want. 1,000,000 is oftentimes pretty good. To give an example of what's going on with this, this is some testing I did the other day of depackage. So the first column there, the first bar graph, is indicating how many executions I got over 60 seconds of depackage just having it compiled with AFL CLang fast, which is notably faster than when you're running it just compiled with AFL GCC, but I didn't actually collect a figure for that. The middle bar here is showing how many executions I got over 60 seconds when I set it to be working in deferred mode. So pushing the instrumentation to the latest point that I thought was reasonable. We ended up going from 13,500 executions per second to 17,200, I'm sorry, not executions per second, executions in a minute, to 17,500. And then finally, that very tall one on the right, that's when you're doing both persistent mode and deferred mode. And in that case, we got 37,400 executions of depackage in just a minute, which is roughly 2.8 times improvement. So you can see that those are very effective techniques for improving the speed of your fuzzing efforts. So now we're going to get back to what I mentioned on those blockers of having too big of a haystack here. So if you have long test cases, they're going to run more slowly, and it's going to be less likely that your fuzzing efforts are going to touch critical data structures. So AFL provides a tool for this. The tmin tool allows you to minimize the contents of your test inputs. It's doing this, of course, by using the instrumentation. You're taking your test input file and running it with different iterative processes going onto it, so character minimizations, and seeing what you can do to the file to shrink it without it affecting that execution path. Sometimes this really isn't going to get you very far, but other times you'll see substantial deflating of your test cases through this. The next tool in the same vein, as I had mentioned earlier, is a tool for actually reducing the scope of your corpus. So if you have a directory full of JPEG files and you want to start fuzzing a JPEG parser, you're not necessarily going to want to use all of those files. The AFL CMIN tool will run through them and identify what the smallest set of test cases to make up your corpus will be, where you're getting coverage of the most features or code paths from the target. And what you get out of this is, as opposed to with the tmin tool, which gives you a single file, you're going to get a directory of what should be a good starting point for your fuzzing. So another performance boost that you can get if you've ever fuzzed something with AFL, you'll know that finding magic numbers and getting to understand the syntax of the whatever file format you're fuzzing, it's time consuming. So what you can do to improve this process is actually build a dictionary indicating the different tokens and other types of complex structures that are going to appear within your target. So, for example, if you want to fuzz MPEG-4, you might go to a specifications document and scrape out all of the atom types and put those values into a fuzzing dictionary. There are examples within the AFL source that you can use to model after, but it's a very simple format. And what this does, of course, is makes it so that if you want to hit the MPEG-4 atom, MOVHD, you don't have to randomly come to aligning all of those letters, but rather it's going to have a stage in the fuzzing where it's just going to be taking values that are user supplied from this dictionary and putting them in. And this will help you expose new feature or new test cases, new paths. So another important thing to note is that if you're fuzzing a target that has checksums in it, so the PNG format, for example, has sections in there that are checksum data sections. If you start fuzzing a PNG, you're going to be wasting a lot of CPU cycles for the most part, because as you change that checksum data, you're just going to end up going to a short circuit through your parser because the checksum isn't going to match. The way to deal with this is to go into the source, find the checksum verification code, and comment it out. For that specific example of PNG files, the AFL source provides an example patch for libpng, which comments out the checksum verification so that you can actually start to fuzz that format. Now, once you've so some of the targets that you're wanting to fuzz, they might not be very conducive for fuzzing through AFL. They might be closed source, or they might just be particularly slow and not good for this, the need for making many rounds of execution to identify your interesting test cases. So the great thing about AFL is that when you've fuzzed one thing, like say we fuzz one JPEG parser, we're going to be able to take the queue that was generated from there, and of course any crashes and hangs, and you can use those as starting points to feed into a fuzzing process that's much more targeted towards another fuzzer. So we'll talk a little bit about examples of how this was used to find vulnerabilities in Internet Explorer, for example, which clearly you can't fuzz directly with AFL Fuzz. So you've been doing your fuzzing, and oftentimes you're going to find, especially if you're fuzzing a target that hasn't been well fuzzed in the past, you'll get hundreds or thousands of crashes. This is a big thing that you need to go through. You need to be able to assess the impact of all of these crashes. So how do we do this? One option is to use AFL. There are some tools in there. There's also the ability to have a faulting and non-faulting test case to compare against. You can use sanitizers, like address sanitizer or memory sanitizer, or Valgrind for that matter. You can use the debugger, so dumping out registers and such. So first, when you've got your crashes, the first thing you'll see is a file format or file naming convention similar to the one that's up on the screen here. You've got a monotonically increasing ID number for the unique crash, the signal that was generated from the crash, what test case was being fuzzed or what path was being fuzzed to produce this, and then of course what operation, what fuzzing strategy that is, and what byte or bytes were fuzzed, or in the case of the splice mode where it's mixing together two inputs, you'll get information on which inputs were being mixed together to form this test case. So the first thing that you're going to want to do is actually make sure that the crash is reproducible outside of the fuzzer. Especially if you're seeing a lot of signal 6s, it's quite possible that it's aborting on an out-of-memory condition. You need to up that -m limit. But assuming your crash does reproduce, your next step is probably going to be to say, all right, well, actually, maybe this won't be your next step. You might want to jump down a little bit further into the process. But another thing that you can do here is to look at the format specification documents to try and understand what the significance of that byte is that has been fuzzed that led to this crash. Tools like JPEG dump and TIFF dump and anything else that's going to give you detailed output about the structure of a file, assuming they don't crash while you're parsing the file, it can oftentimes give you very quick information about what particular attribute of the file or parameter in the file has been changed that led to the crash. It's also helpful here to be able to go back to that parent path test case, so meaning you take that source number and you go to the queue and you find the file with that ID number, and then you have a file that was the direct descendant or direct precedent of the crashing test case. So if you can look at the value from that byte and have some meaning assigned to it in the non-faulting test case compared to the faulting test case, might give you a better idea of what's going on. Sometimes, though, you're going to want to explore a crash a little bit more. So AFL actually has a mode that you can invoke through the -Big C option, which is going to make it so that you're fuzzing and you're looking for unique crashes and you're discarding anything that's not resulting in a crash. The idea here is that you might be able to start to see whether or not you have control of different registers and get an idea of what this crash is all about. So moving on to sanitizers, as I mentioned, address sanitizer and memory sanitizer, these are very good tools. They're actually included with modern compilers. So GCC and CLang both have them in there now. You can add this into your compile by setting C flags with the -F sanitize and then address or memory as the value depending on what you want to do. When you're using memory sanitizer, this is going to be helpful for recognizing uses of uninitialized memory. Address sanitizer, which is what I'm generally using, is going to be tracking all of your memory and tell you about use after free conditions and different other exploitable conditions. You can see here on the bottom some output from one media library that I was fuzzing, and you can see that it's telling you plain as day there's a stack overflow here. So the sanitizers, to think about this with some older technology, it's like Valgrind, but rather than running in your emulated environment, you're putting this in at compile time. And the program is just going to be halted as soon as there's even the most subtle memory corruption or misaccess to memory. So say you've got an overread condition that's just reading an extra 4 bytes off a variable. Normally that's not going to crash your program. Neither would writing an extra 4 bytes, perhaps, depending on where it is. But with address sanitizer, you will recognize that test case. You could actually use this all the time and have very good security on your applications, but it does have a performance hit, roughly 2 times performance degradation, and also it has a much higher memory envelope because it needs to maintain a lot more metadata about your allocations and the usage of different structures. So here is a slide showing AFL or address sanitizer output from something I found with AFL. This hasn't been disclosed yet, which is why or hasn't been fixed yet rather, which is why it is redacted there. You don't see the stack trace, but in the top half there, where you can see addresses related to a stack trace, you would also get information, if available, about the symbols in the binary, and enough to generally figure out where the variable was allocated, where it was used, and track down your bug. Another powerful tool that's a little bit more lightweight is going to be GDB, of course. Within the AFL code, you've got an example script in there for triaging crashes. What this is going to do is go through your crashing test cases, and for each one, run GDB, let it crash, dump out the registers, disassemble around the program counter, and give you a backtrace for recording. You might need to make some minor tweaks depending on what your target is. Like if it's not using standard input, you're going to want to modify it so that it's taking as an argument a file location. Another tool that I use is the GDB exploitable plugin, which was originally a cert triage tool. This is nice because there's not much thought involved with it. You're not looking at registers and thinking about the disassembly and what might have happened here. Instead, it's going to automate that process and give you an exploitability classification. Like you can see here, it's saying for this particular bug, which was in a compression engine, it's probably exploitable, which would be a good reason to investigate it further. In my environment, what I tend to do is some basic bash for looping, where I go through each test case and I use GDB to do something basically the same as what that triage crashes script is doing. And then I also run bang exploitable to save that output off, as well as running an ASAN compiled version of the binary and outputting the ASAN report to files. So in this way, I can very quickly grep through the files in the directory looking for different keywords that are going to come out from this output, like overflow, exploitable, probably exploitable, and recognize the most interesting crashes there very quickly. You can also, of course, make updates to the triage crashes script to use bang exploitable and ASAN. So the results of AFL are really quite impressive. This list that's up here, it's all of the different things that are in the AFL trophy case. So this is by no stretch of the imagination all of the things that AFL has been used to find bugs in, but it is some of the more notable security bugs that have been found in it. Too long to list through, but we will talk about a couple of them specifically. So first of all, everybody knows shellshock. When shellshock was not found with AFL, but when shellshock was found and the patch came out, Alcamptif worked and used AFL Fuzz to very quickly find new code execution bugs within bash related to environmental variables. Of course, in order to do this, it just took some slight tweaks to bash so that it would be reading the environmental variables from standard in. You can read all about this on Alcamptif's blog, and actually within the AFL source, he's got the diff file or the patch that he applied to bash in order to make this work, and some instructions about how to use that. Heartbleed, another name brand vulnerability here, also not found by AFL, but it could have been found by AFL. And in fact, Hanno Beck, he did some research and showed conclusively that without knowledge of where to look for Heartbleed, you could take OpenSSL and make various modifications from it and locate Heartbleed. So in order to make this work, since Heartbleed, of course, is an overread condition, it's not going to cause a crash, he needed to be using ASAN. I mentioned before that ASAN doesn't play real well with AFL, but in 32-bit mode you can do it, and also if you disable the memory limit, as Hanno did, you're able to make AFL work with ASAN and crash when it hits a heap buffer overread, as was the case with Heartbleed. Another hurdle to overcome here, though, which is perhaps something that many of you might encounter if you want to start fuzzing network applications with AFL, you've got the problems that AFL is designed to take input from files, not network sockets. So in order to work through this, the application was rewritten slightly to make a standalone app that was taking advantage of files to pass along messages and be able to fuzz those message formats. And it did, in fact, find the buffer overread condition within the Heartbeat extension. So one more example result here. I mentioned that AFL had been used to find bugs in Internet Explorer. Specifically, one example of this is the use of AFL to find ASLR bypasses or information leaks within Internet Explorer and other browsers. The way that this worked is that you start with an open source image parser or some other format that the browser is going to consume, in this case images though, and you generate a synthesized corpus from it, and then there is some HTML and JavaScript that LCampTIF put together, which is in the AFL source, which is going to iterate through all of the files in your test corpus. And first, you load up an iframe to just kind of populate the memory with some data. You create an HTML canvas on the web page, and then with the JavaScript, you keep on loading that graphic, rendering it to the canvas, and reading back out the output to see whether or not it's changing. The idea here is that if the output is non-deterministic, like if your graphic renders one time with data dump A and another time with B and another time with C, it seems very likely that it's making use of some uninitialized data. And this could mean that you're getting values off of the stack. You could have addresses in there which can be very useful for crafting an exploit. And since an attacker can actually read that back off through the base64 output of the image on the canvas, this is a viable attack vector. So this is now the time for questions. Does anybody have anything that they'd like to ask? Okay. All right, so the question was, how long does it take you to go from finding an exploitable crash to actually writing an exploit for it? So from finding a crash to seeing if it's likely exploitable is very quick. If you're using address sanitizer, for example, to actually conclusively confirm that it's exploitable, that's going to vary quite a bit based on what it is that you're looking at. If you're familiar with the file formats, you can quite possibly do that pretty quickly. When you're looking at something that you're not as familiar with, like I've looked at some things that seem to be exploitable with the Perl-compatible regular expressions engine, which I still haven't been able to actually demonstrate, for example, being able to take control of VIP. But with some other things like there were fuzzing efforts that on the libtiff tools, LCampTIF had posted onto Full Disclosure quite some time ago saying that nobody should be using these because there are so many holes in like the various tools. With TIFF dump, for example, I had gone very quickly from finding an exploitable condition to demonstrating control over EIP, like an hour for me, but other people can probably do it faster. Any other questions? All right, thank you everybody for your time. And
thanks again, and again on behalf of BSides, and thanks to our sponsor Fitbit, I want to present you with a Fitbit.
thank you.
Thank you again. Appreciate it.